Hi, and welcome back to our flipped chemistry classroom where we're continuing our conversation about gases and we're introducing the gas laws. So we're going to learn about 3 different gas laws today that explain the relationship between pressure, temperature, and volume of an ideal gas. So this is just a reminder that an ideal gas is any gas that perfectly fits all of the 5 assumptions of the kinetic molecular theory. So again, quick reminder, 5 tenets of the kinetic molecular theory. They're really, really far apart relative to their size, and they are in constant random rapid motion. The collisions between gas particles and the walls of the container are elastic, which means no kinetic energy is lost. And those collisions are what cause the pressure of a gas. Our gas particles are in constant random rapid motion. There are no forces of attraction between our gas particles, and the average kinetic energy of gas particles depends on their temperature. It's directly proportional to their temperature. Okay, so 3 laws that we're going to learn that relate pressure, volume, and temperature. And we're going to assume that these apply to gases in our class. We'll talk about when gases are not ideal, and then we'll talk about exceptions. But for right now, we're going to assume that these laws apply. So the first one is Boyles Law. And Boyles Law says that pressure is inversely proportional to volume when temperature is held constant. So we can express this mathematically by saying that the initial pressure times the initial volume is equal to the new pressure times the new volume. So if any one pressure or volume increases, the other one has to decrease in order to keep it constant. And so we actually can graph this. In reality, it's a little bit of a curve. You probably drew it in our simulations as a straight line, but that's okay. So let's do a practice problem with that equation. Remember, our equation is P1V1 equals P2V2. So here's our practice problem. And the practice problem says, what pressure would have to be applied to compress 23 liters of gas into 2 liters of gas, assuming the initial pressure of the balloon is 1.05 atmospheres. So we have an initial pressure of 1.05, so that's our P1. We have an initial volume of 23 liters, so that's our V1. And here's our V2, and we're looking for P2. So we're going to just plug that in. Volume times pressure is equal to the new volume times the new pressure. And when we solve that, we would find that we would have to increase the pressure to 12 atmospheres. So we'd have to apply a lot of pressure to condense this balloon down from 23 liters to 2 liters. So that's Boyles Law. Pressure is inversely proportional to volume when temperature is held constant. So now we're going to talk about Charles's law. And Charles's law says the volume of a temperature is directly proportional. Volume of a gas is directly proportional to temperature and extrapolates to 0 at 0 Kelvin. And again, we're holding pressure constant now. So we express this mathematically by saying that the initial volume divided by the initial temperature is equal to the new volume divided by the new temperature. Remember, as we said at the beginning of this unit, when we're working with gas laws, temperature has to always be in Kelvin. So we have to convert from Celsius to Kelvin if we're given Celsius. And if we were to graph Charles's law, as temperature increases, so does volume. So here's our practice problem. So it says, how hot will a 2.3 liter balloon have to get to expand to a volume of 400 liters? And we're going to assume that the initial temperature of the balloon is 25 degrees Celsius. So we have a temperature, an initial temperature, but it's in Celsius, so we're going to have to convert it to Kelvin. We're going to have to add 273. We have an initial volume. We have a second volume, and we're looking for a second temperature. So we're going to plug this in. V1 over T1. Notice that I've converted T1 to 298 Kelvin. That's 25 plus 273. And here's our new volume, 400 liters, and our new temperature. And we're solving for the new temperature. And we get that our new temperature is 51,000 Kelvin. So that's really, really, really hot. I think our balloon would melt before we got there. But Just a practice problem. Okay, last one for today is called Gay-Lussac's law. And this is that the pressure and temperature of a gas are directly proportional, provided that volume remains constant. So if we keep volume constant, we have a rigid container, and we increase either pressure or temperature, the other one is going to increase as well. And once again, temperature has to be in Kelvin. So again, because this is a direct relationship, when we graph this, we get a line with a positive slope and increasing slope. And one more practice problem. So we have an unknown volume of gas at a pressure of fixed volume of gas at a pressure of 0.50 atmospheres and a temperature of 325 Kelvin. If we raise the pressure to 1.2 atmospheres, what will the new temperature be? We're holding volume constant. So our pressure 1 is 0.50 atmospheres and a temperature 1 is 325 Kelvin. We're increasing the pressure to 1.2 atmospheres and we're asking what will the new temperature be? And so we find that our new temperature is going to be 780 Kelvin. And that's how we solve those problems. As always, I look forward to hearing your questions and seeing you in class.